All right, thank you. All right, hello guys, and welcome to class again once more. In today's lesson, we'll be looking at functions, the aspects of injection, surjection, and bijections. So we'll start by looking at what is a function and what is not a function. This one is very important, and I'm sure we have done part of this in secondary school. So not all relations are functions. Injective, surjective, and bijective just tells us about how a function behaves. We are going to discuss all of that. And a function is a way of matching the members of set A onto set B. And let us remark, let us look at the following. I'm going to show you what is a function and what is not a function. Now let's consider this relation where the elements of set A are mapped onto set B. So here we have set A and that's set B. So this set is called the domain. How do we call this other one?
The codomain.
All right, so this is the domain and this is the codomain. So when you look at the relations from set A to B, if you look at this first element here, it is mapped onto two elements, right?
Yes,
Yes,
sir.
sir.
And this second one is mapped onto just one element and just one element. Any relation in which one element from the domain like this is mapped onto two or more elements is not a function. I repeat, for any relation like this in which one element in the domain set is mapped onto two or more elements like this one, it's not a function. This is a relation, but it is not a function. So this type of relation is called a one-to-many. One element here is mapped onto many. So all one-to-many relations are not functions. Are we together, guys?
Yes, sir. Good evening, sir.
Yes.
All right. So is this a function or not, and why? Welcome to those who are just joining. So this is not a function for the reason I have given, because one element in the domain is mapped onto more than two or more elements in the co-domain. So it's not a function. It is a one-to-many relation. Now let's look at this other one. In this particular case now, we have each element in the domain has only one element in the codomain. But we see that some two elements in the domain have the same element in the codomain. Can you see this?
Yes, sir.
Yeah, this type of case is a function. So members from this first set should have only one, should be related only to one element in the other set. One element from this domain should not be related to two elements in the codomain. But many elements from here can be related to one element, like this one. This one is a many to one. Many from here, one from this side. So we say many to one. So many to one relations are functions. Normally, this is a general function, and this is a relation in which we have many being mapped onto one. Each element has an image. So this is how a function is generally represented. So in general, all one-to-one relations and many-to-one relations are functions. All the other ones are not functions, like many-to-many or one-to-many. Any questions?
No, sir.
Right, let us go ahead. Let's look at some examples of injective, surjective, and bijective functions. Right, so here, let us look at this.
So there's too much noise here, sir. You can mute somebody microphone.
Right, I'm trying to mute. Roderick, noise from your background. All right, the noise has gone. All right, let's look at this relation. Here we have one-to-one relations, right?
It's not from me, sir.
All right, it's not from you, sorry. So we have one-to-one. relations here. So this is a function, one-to-one, and one-to-one relations also have another name. This is a special name that they have. One-to-one relations are also called, or they are set, the function is said to be injective if it is one-to-one.
Injective.
Yes. So this is an injection. Since it is one-to-one, we say it is an injection. But this particular function is not surjective. And I'm going to give you the reason why it is not surjective. It is not surjective because two elements from this domain do not have the same image here. Can you see? Secondly, all the elements of this codomain have not been used. Look at this element. This element does not have a pre-image. This element has not been used. Since this element has not been used, we say this function is not surjective because this element has not been used. So the main reason here is that all B have not been used. Let's look at the second one. What type of relation is this? Is it one-to-one, one-to-many, many-to-one, or many-to-many?
It's one-to-one.
Look at it very well again.
Many-to-one.
Yes, it is. It's many-to-one now.
So I'm not seeing the image yet.
You are not
Okay.
seeing it.
Okay, so I'm singing now.
Yeah, so this is many-to-one. You can see many of them, two of them here have the same image. So this is a many-to-one relation. So this is a function as well, and it's a many-to-one relation. It is surjective, and all the elements in B have been used. If you look at the domain, sorry, the codomain, all the elements have been used. So that is why it's surjective, because all the elements have been used, and it's also many-to-one. So this is not injective. Do you know why this relation is not injective?
So because there are no two, because two elements from the domain are mapped to one element in the codomain.
Perfect. So because it's a many-to-one relation, and that is what you have just explained perfectly. That is why. So two elements should not be mapped onto the same element. Yeah. So this makes it now many-to-one. Thank you so much. Now, what about this one? This one is one-to-one and also many-to-one now. So this is one-to-one, and is it many-to-one?
So all of them are one-to-one.
Okay, it's all one-to-one. But now there is something here. Why do I say that this function is bijective?
Those I can't find your notion.
I don't run good after that.
What?
You don't have time for that.
All right. So why am I saying that this function, this relation is bijective? Guys, are you there?
Yes, so we're there.
So why is this particular function or this relation bijective? Why is it a bijective function?
So because for me, because two elements in the domain cross on each other.
If I can decide and put it to be straight lines, it will not change anything. So this is the reason. This place here tells you the reason. So it is a bijection because all the elements here have been used.
Because.
So a function is bijective if the codomain is equal to the range.
Okay.
Yes, the codomain here is equal to the range, right?
Yes, sir.
Yes, because all the elements in this set have been used. So that is why it is bijective. Sorry, that's why it is surjective. All right.
So I have a question.
So this particular relation is injective. It's 1-to-1.
Sir,
Yes.
so I want to ask something.
Yes.
In this, when a function is subjective, all b are used. Was it not supposed to be all y are used?
All right. If you consider the sets to be A and B, there's no problem. I consider this one, we are considering it to be the B. So I was just saying that this one like this gives us the idea. If you look at this, you can give you the answer. Normally, throughout this lesson, we'll be talking about using the sets A and B. This is set A as for the domain and set B for the codomain. So I'm sorry I did not say that. Are we together? So all elements in the codomain have been used. Any question, guys? Some people are not saying anything even.
No question yet, sir.
Yes, God bless. Welcome to
None,
this
sir.
class. How are you today?
So there's no question.
All right. Let us go ahead. Let us start getting to the tough things of the matter now. All right. Now we are looking at how do we call this?
Noise somewhere.
Yeah. So in general, a function is injective if it is 1-to-1 and all the elements in the domain have been used up. You see, it's injective. Then it is surjective if all the elements in the range have been used up, or if the codomain is equal to the range. So equally, if it is many to one, then we say it is surjective, but all the elements in the domain should be used. And equally, a function is bijective if it is both injective and surjective, like you saw in that last example. So 1-to-1, let me see, one-to-many and many-to-many relations are not functions. So 1-to-many and many-to-many. In fact, when it ends with many, it is not a function. All right, now let's start with injective functions. So a function is an injection if f of x equals f of y implies x equals y for every x, y, an element of R. So this is a definition for injective function. If they say you prove this, what you will use to prove. If f of x equals f of y implies x is equal to y for every x and y, an element of the set of real numbers. Let's take an example to prove that this function 2x plus 1 over x minus 4, where x is an element of the set of real numbers and x should not be equal to 4, is an injection. Also find the inverse of this function and state the domain of that inverse. This is a past question, advanced level.
So I see.
All right. How can you see? How do you know it's a past question?
So I've seen it. I've scrolled through a lot of past questions.
Okay, that's nice. So the first thing, we have to use this conditional f of x equals y. So in this function, this is already f of x. Now let us look for f of y and equate to it. So this gives us 2x plus 1 over x minus 4 to be equal to 2y plus 1 over y minus 4. So our issue here is we are solving to see if we arrive at this answer, that at the end, x is equal to y. If at the end we arrive at this, then this function is a 1-to-1 relation or is an injection. So we simplify, we cross multiply, you have x minus 4 times 2y plus 1 to be equal to y minus 4 times 2x plus 1. We expand. When we expand and simplify, this is what we are going to have. Let me know waste time. Now, we have 2xy on the left-hand side, 2xy on the right-hand side. The 2 cancel out when we bring 1 to the other side. We equally have minus 4 on both sides. So these ones will also disappear or be eliminated when we bring 1 to the other side. We'll be left with x minus 8x When we bring this one to the left hand side, it becomes 9x. This one should be equal to, if you carry this minus 8y's, or we say we add 8y's on both sides, on the right hand side, we'll have 8y's plus y, which is 9y's. And from here, x is equal to y. Therefore, this function is injective. That is all about injection for everything that they give you. So you just follow these statements. Look for f of x and equate to f of y, and solve until at the end you have x equals y. Then you conclude. If x is not equal to y at the end, you conclude that the function is not injective. Question.
They say find the inverse.
All right.
State it.
All right. So let us find the inverse. To find the inverse just means you solve for x now. So we just
Yes,
let this f of x be y, or we can solve it like that. So we'll have y, this f of x is now y, is equal to 2x plus 1 over x plus 4. We cross multiply. This is what we are going to have. We expand, simplify, and bring like terms together. I will be explaining this and wasting your time. So this is what you have for x when we solve in this function. So what is the domain? Or let us first of all get the inverse function to be f inverse of x equals 4x plus 1 over x minus 2. So this is the inverse now.
yes.
So other guys are not speaking. Are we actually in this class together, or some people are just there and they're not saying anything? Lina,
Let's say
speak now. Let me hear. Rodrigue, Collins, Gilead, Roger. All right. So what's the domain of definition of this function, of this inverse function?
The x should be all real numbers except 2.
Perfect. So the set of all real numbers excluding 2. And since it's a rational function, we equate this denominator to 0 and solve for x. So x should not be equal to 2. Yeah. Some people just write it like this, but I will prefer that you should write R except the set of all real, except 2, sorry. The set of all real numbers
except 4.
Yeah, except 2. Like this. Where can I even write? There's no space on this screen. So we have the set of all real numbers, excluding 2. We put a 2 in this curling brackets or braces, how they call it. So I write it like this. So this is it for injections. For your back, most of the time you see these questions that you show that the function is injective. And equally for advanced level, you mostly see this as way to show that it's injective. Normally, they hardly ask for surjective, but let us look at surjective. Yeah, surjective is going to be very sweet, so you have to really pay attention. I hope you understand what I mean by sweet.
Yes, sir.
So a function f is surjective if for every x an element of A, there exists y an element of B, such that f of x is equal to y. Note, A here is the domain, B is the codomain.
So what's the meaning of this sign, this opposite E?
If there exists.
Okay, sir.
Yeah, so I'll read this as a function f is surjective if for every, this A that's upside down means for every x, an element of A, there exists y, an element of B, such that f of x is equal to y. Let us take an example to explain this definition. So let's set A, this equation, let's set A be the set of all real numbers excluding 3, and set B the set of all real numbers excluding 1. Consider the function f is such that A is mapped onto B, given by f of x equals x minus 2 and x minus 3. Is this function surjective or not? Another name for surjective is onto. Are we together?
Yes, sir.
Yeah, so it's onto, we say it's surjective. I don't know why the spelling is O-N or U-N. All right, so we start by saying that since we want us to show that this relation is onto, we start by saying that by looking at this y that exists. So there exists a y, an element of b. That's where we start with. So let us have a y, an element of b. And they have given us b here. They have defined b as a set of all real numbers excluding 1. So let there exist a y, an element of b, where b is a set of all real numbers excluding 1. And we know that y should not be equal to 1 from this definition. So the next thing is, then the function f is onto if there exists x an element of a such that f of x is equal to y. All right. So this, if you can see this definition here, this is it. So we start by using this second middle part of this definition, and then we move now to this end. So let us continue now. So from here, we are going to consider f of x equals y. When you are doing this definition, when you're proving, you might not need to say all of this, this second line and all these sorts, the other things. So let us start with this function here. So let this f of x, this f of x, let this be equal to y. So most technical students will just start from here. Let f of x be equal to y. This implies that y into x minus 3 is equal to x minus 2. From here, we will have our x to be equal to this. This is our x. This x, right?
Yes, sir.
Now, what's the domain of definition of this one?
So y is not equals to 1.
Now, the domain of this inverse function, this is the inverse function, right?
Yes, sir.
Yeah, because we have solved for
Yes,
x
sir.
from here now. Yes. What we are doing here is we are looking for the inverse function. This is the inverse function. X is equal to this. And what is the domain of that inverse function? All real numbers excluding 1, right?
Yes, sir.
Yes, sir.
Now, from this question, what is the domain of the codomain?
One.
All right, the set of all real numbers excluding 1. So this is the codomain, the set of all real numbers excluding 1. And from here, what is the range of this function? Another name for this is the range, right? The domain of the inverse function. So the domain of this inverse function is a set of all real numbers excluding 1, which is equal to the codomain. Do you now grasp the concept?
Sir, please come again.
All right. Let me give you a shortcut. So a function is surjective if in f is equal to cot f. Do you understand this? Now from this question, this is the codomain. The codomain is this set of all real numbers excluding 1. Can you see this?
Yes, sir.
And now, what is the range? F is the range or the set of all images. What is F? It's also the set of all real numbers excluding 1.
F is equals to
Set of all real numbers excluding 1. Now, is this codomain equal to the range? Yes or no? Now look at it. This is the range. Yes, they are equal. This is the range set now because this is the inverse function. The inverse function is the domain of this inverse function, which is the range, is the set of all real numbers excluding 1. And what is the codomain of this function that was given in the equation? The codomain is also the set of all real numbers excluding 1. So from here, you can see that the image or the range is equal to the codomain. So what do we conclude? That this function is onto now.
Yes, sir.
So normally, to show that a function is onto, you can just start from here. You look for the inverse function. When you look for this inverse function, you get the domain of the inverse function, also called the range. And then you check if this range is equal to the codomain. This is the codomain. So if this range is equal to the codomain, then this function is onto. Are we together, guys?
Yes, sir.
So that's the end of surjection. So a function is surjective if the codomain
Yes, Mama.
is not the range.
Mama.
You're calling maths come and tell the class.
Sorry.
All right. So for this point, so this is the range, the set of all y's or all real numbers excluding y equals 1. And this range is the same as the codomain here. This is what we defined here. Y should not be equal to 1. And that was the codomain. Here equally, the range is also y should not be equal to 1. So we conclude that therefore this function is onto. You can verify your answer here. Now let's verify and see. Let's check and see if this answer is true. We check by saying thus any y an element of B, there exists this. We are going to take this value and fit inside this f of x equals y. We'll fit inside this f of x that we have obtained and see if we obtain y at the end. So these are f of x here. And we know that x equals to 3y minus 2 and y minus 1. So let us take this value and substitute it here. So we have f of 3y minus 2 and y minus 1 should be equal to, when we substitute, we have that this position minus 2 over this x value minus 3. When we simplify all of this, this is what we obtain. And this is equal to y. So it matches now with what we wrote here before. F of x is equal to y. So we conclude that this is onto. So here I was just checking and showing you how you can check. Right, so I'll please that you go through the notes, and if you have some questions too on onto functions or relations, then you also look at them. If you say you should prove that the function is bijective, you have to prove that it's injective and also prove that it's surjective. So you need these two steps. You use the first step for injections and the second step for bijection, for surjection rather. Then you can prove it. All right. Let me take the next thing that we have here. Somebody asked me a question on curve sketching, right?
Yes, sir.
Yeah. Okay, I think let me see if this is the question here. And there's another one that we'll look at. Please, during the week, if you have questions, you try to send them. If you have questions, you try to send them so that on Sunday we can go through. You can send them to the group or leave a link that you can upload them so that on Sunday we can go through. I'll leave the link on the website. I'm trying to look for it, please. No, not this one, not this one. One. All right, let me try to get the page I'm looking for. I don't know how I saved this thing. Question 9. All right. All right. They gave me this one. They forgot to remove the voice behind. All right. Let me open from here. Will you take down the question number? All right. Yeah, this is the question. So this is the question. We have June 2019, paper 2, as you can see. And the question reads that I'm concerned with this second part, this part in red. So you are given the function 2x plus 1 on x minus 4. I think this is x minus 4. Sketch the graph of this function, showing clearly all its intercepts and the behavior of the curve as it approaches its asymptote, 6 marks. Are we together?
Yes, sir. So why are you not solving the first part?
This one of the differential equations.
Oh, so it's okay, it's okay.
All right. So that's why just focus on the second one. So let us look at this question. So with this question, we can start by this the function, right?
Yes, sir.
So for the domain, we have the domain, we equate the denominator to 0, or we inequate the denominator to 0, and x should not be equal to 4. So the domain of this function should be the set of all real numbers excluding 4. That should be the domain of this function, the set of all real numbers excluding 4. All right, then, and we can write it in interval notation. I wrote this one in interval notation from negative infinity to 4 from below. Then we continue from 4 from above to positive infinity. Technical school students, I hope you understand all of this.
So maybe just explain it again.
Because nobody's saying anything. We look at domain of functions before, right?
Yes, sir.
So
Yes,
domain,
sir.
there's a set of all real numbers excluding 4. I have decided to write the answer in interval notation like this. From negative infinity to 4 from below, as you can see, is outside. Then we continue 4 from above to positive infinity. That's the domain of this function. Now the next thing is for us to take limits at these boundaries. How many boundaries are here? We have this boundary 1, 2, 3, 4. So there are 4 boundaries. So we need to take limits at 4 points. So we can, for this function, we can we can combine the limits at negative infinity and positive infinity, and there will be no issue. Now with the rational functions, to get the limit at infinity, please listen attentively. The limit at infinity, we divide highest degree by highest degree. The highest degree in the numerator is 2x. That's the term with the highest degree. And the denominator, the term with the highest degree is just x. So to have the limits, you just take the highest degree, that is 2x, divided by x. Because if x tends to infinity, you add 1 to it, it will not really change anything. Or you subtract 4 from it, you will not change anything. So you just consider the highest degree. That is why. So from here now, 2x divided by 2x will give us 2. So the limit of x, yes, please. Any question? Pardon? The people who gave me this question, they're not saying anything. Did they even solve?
Negative.
Gilead, Collins, Roger.
Yes, sir.
Yes, you have a question, ask. So when you are taking limits at infinity, only at infinity, we can take highest degree divided by highest degree. If it's a rational function.
So then how come you had 2x on x? I'm not really understanding the lim stuff because I've not done it.
All right, limit means how does a function behave if x becomes very, very, very big? Like, let's take, for example, take a number like, for example, 1 million. 2 times 1 million is 2 million now.
Yes, sir.
2 million
Yes,
plus
sir.
1. 2 million plus 1, will it really change anything? It's just the same like 2 million, right?
Yes, sir.
That's why
Yes, sir.
that's why I've written just the 2 million here. Now, if x is 2 million, can you see now? Sorry, 1 million. 1 million minus 4. You will not really change anything, so I can just consider approximate it to just 1 million. Can you see?
Yes.
That's why I've written just the x here. Now 2 million divided by 1 million is 2 now.
Yes, sir.
So if the number becomes very big, you can even use a calculator. You can even take 100 billion or 10 million and put here, fit in the numerator and put the denominator. You see that the answer will be approximately equal to 2. That's the meaning of limits at infinity. Are we together now?
Yes, sir.
Normally, we have not reached this topic, but somebody asking the question and so on. Actually, I emphasize that they should ask questions as we go ahead with topics. But I don't know, maybe this can motivate some students to study. Who knows? Then we now have to take limits as x tends to 4 from below. Means you can take a number that is very close to 4, but not equal to 4, like 3.99 or 3.9. Normally, since x is not, this function is not defined when x is equal to 4, it means that the limit at x equals 4 will be infinity. So the answer here, we already know that is infinity, but we don't know whether it's positive infinity or negative infinity. Are we together?
Yes, sir.
Yes, sir.
So for any value of x that the function is not defined, when you take limit for that value, the limit must be infinity. But you always need to know whether the infinity is positive infinity or negative infinity. If you take the wrong one, the function will go in the wrong direction when you sketch it. So here, since we are taking 4 from below, we'll take a number that is very close to 4, but not equal to 4. Choose any number. You already know the answer is infinity. You want to test to see by the sign of the infinity. That's why I've taken 3.9. You can take 3.99, you can take 3.8, but take it very close to 4. So if you fit the values here, 2 times 3.9 plus 1 is positive, and 3.9 minus 4 is negative. Positive divided by negative is a negative number, so we have negative infinity as x tends to 4 from below. This is how they write it below, or some people put a minus here. Like 4 to the power minus 1, but it's not actually minus 1. Now we have to take another limit as x tends to 4 from above. So we can take now 4.1. So we can take 4.1. That will give us. Okay. So we think now at 4.1. Let us now use 4.1 and see. All right, 4.1. So we take 4.1. I have 2 times 4.1 plus 1. That is positive. And 4.1 minus 4 is positive. Positive divided by positive is positive. So this gives us positive infinity. So we start with the domain. We move to the limits. We can now look at the asymptotes. You know about asymptotes, right?
Yes, sir.
There are 3 types of asymptotes. You have vertical asymptotes, horizontal asymptotes, and oblique asymptote. In fact, horizontal asymptotes are a special type of oblique asymptotes in which there is no variable in it. The asymptote is a constant. We'll look at all of that, don't bother when we look at curve sketching. That will not be long from now. So the next thing now we have the vertical asymptote here. From the domain of definition, you always see the vertical asymptote.